Okay, this one also comes out of section PD, which was properties of dimension. This is another example because, as I indicated, there's just not a dearth of good homework problems from section PD. So I've saved those for homework, and we're going to use as samples some of the examples. All right. Well, this was a previous problem where we basically found that B was a basis for this particular subset. It was basically Z, and Z was a generalized 2 by 2 matrix. That is, it came from the set of M22, but with this specific relationship between A, B, C, and D. Both these linear equations had to be followed, where A, B, C, and D were all elements of C. I'm not going to go through the proof of that now. This was a previous example, so that this definitely is the basis for this set. And that means the dimension of Z is 2 because it takes 2 matrices in order to span this set. Our goal here is to find another basis. Remember, a basis isn't unique. What is unique about it is its dimension. So we need 2 more 2 by 2 matrices that will also span this particular set. So let's find those. Turns out to do it, all we need is a linear combination of the 2 matrices that make up B. And they can be randomly selected. So I'm going to randomly select 2. I'm going to go 2 times the first one, negative 2, 1, 1, 0. And again, this is purely random, minus 1 times the second one, which is negative 2, 0, 0, 1. And we can see what that makes when I add up the 4 elements of the product. I'm going to get negative 2, 2, and 2, negative 1. So that's the first of the 2 matrices. For the second one, again, I'm going to do the same product. I'm just going to pick 2 more random numbers, 3 times the first one, which is negative 2, 1, 1, 0. And for the second one, minus 2 times the second one, which is negative 2, 0, 0, 1. And this time, I'm going to get negative 2, 3, 3, negative 2. And although this is a symmetric matrix, there isn't anything I did to try and make that happen. These were entirely randomly selected. Okay, so that means our new basis, B prime, which should also be a basis for the subset Z, is going to be negative 2, 2, 2, negative 1, followed by negative 2, 3, 3, negative 2. Now, how do I know that this is a basis? Well, we know it's a subset. That is, B prime is a subset of Z. And I know that because if B was the basis for Z, then any linear combination of B formed all of Z, and this is one of those. So B prime has to be a subset because we got it from the old basis. So it ticks that box. You know, to be a basis, first thing a set has to be is a subset of the original. So it is. Second thing I have to check is whether it's linearly independent. And remember, to check that for matrices, it's the same as checking it for vectors. I have to check A times negative 2, 2, 2, negative 1, plus B times negative 2, 3, 3, negative 2. And I have to see how many solutions of that produce the zero matrix. So it means I'm going to form a system of 4 equations with 2 unknowns. I'm going to skip to the part where I just have the coefficients. The coefficients are going to be negative 2, negative 2, 2, 3, 2, 3, and 1, negative 2. So that's the matrix I get from the coefficients of A and B that make this true. Let's take the reduced row echelon form of this. And when we do that, we get 1, 0, 0, 1, and 2 rows of zeros. And what does that show me? That shows me that A and B have only trivial solutions to make this true. That means this set is linearly independent, and we already know it's a subset. It's got the same dimension as the original basis. And what does all that mean? Well, by theorem G, this Goldilocks theorem, this checks all the boxes. That means B prime is a basis of Z in all 2 by 2 matrices.